We'll start the recording right there. All right, so this is the one we did last time where we wrote out our reactants here based on the compounds that we were given and then identified how these could be swapped. All right, so we have potassium and hydroxide were one of our starting compounds, and then potassium and bromide, one of our possible products if we have a reaction, which we did in this case. Then nickel and bromide. So we had nickel hydroxide as one of our possible products, and we saw that that was insoluble. Okay. So let's say we have a solution of ammonium chloride and iron nitrate mixed together. Right? So we're taking two probably clear liquids and we're mixing them. We can start by just writing out all of the ions, or each of these compounds. So ammonium is NH4+. We're going to have chloride, so Cl-, and then iron nitrate. And then iron has a 3+ charge because of the Roman numerals there. And then nitrate. So you can see why I have you memorize the polyatomic ions. They're going to come up a lot this last time. All right, so those are all of our reactants. And there are two ways that you can approach this, right? We need to know if we're getting an insoluble product. So we could combine these and see what those starting reactants are, properly balanced. But we don't have to do that to figure out if something's going to be soluble. So we can actually do that first. And the way we do that is we take our cations and we move those over together. Oh, I actually drew that wrong. Move those over in the same order. So if ammonium is here first, we're going to put ammonium over here. And so that'll be combined with something. And then we'll have iron, 3+, plus whatever the other anion is. Right? So we just swap our anions with our cations. So now we're going to get ammonium nitrate and iron chloride. Whoops. Nope, that's not what I wanted. I want this. There we go. So now we can go back to our solubility table and look for ammonium nitrate and iron chloride. So hopping over here, we were looking for ammonium nitrate. Oops, that's a 4. We haven't balanced these yet. And iron chloride. So real quick, you can find ammonium is up on top, and there are no exceptions for its solubility. So ammonium nitrate's definitely going to be soluble, especially since you can also find nitrate here, which also has no exceptions. Then for iron chloride, you see that actually chloride is generally soluble, and the only exceptions are silver, mercury, and lead, which we actually don't have any of those. So do we have a reaction? If both of these are soluble, is there a reaction? Right, no reaction. So there's nothing left to do there. So those ones go pretty quick if you can do this first. Won't always be the case though. So we've got another solution, or another problem where we're mixing two solutions. We're going to have potassium sulfate, K+, SO4 2-. and strontium nitrate. And again, even before we balance these compounds, we can go ahead and swap the anions and see if we're going to get an insoluble product. So right, potassium plus nitrate. So I'm also writing these out right now with the charges because we haven't combined them yet. Also sort of as a reminder that this is not balanced yet, right? We're not done if this does have a product. So I need to bookmark this page. All right, so we're looking for potassium nitrate and strontium nitrate. Sorry, not strontium nitrate. Strontium sulfate. Sorry, wrote the wrong one in there. Yeah, now we're good. Okay, so potassium nitrate, strontium sulfate. So potassium, let me erase these ones now. We're going to have potassium nitrate and strontium sulfate. So again, potassium nitrate, always soluble. So you don't have to worry about any of those.
May I have your attention, please? This is Atlas IED.
But sulfate, on the other hand, generally soluble, but we have an exception because this is strontium sulfate. So strontium is one of our exceptions. So when sulfate pairs with strontium, the compound is insoluble. So that means we do have a reaction in this case. So now we do have to go through and balance these, not only the individual compounds, but also the whole equation. So on the left side, on our reactant side, we're going to have potassium sulfate. So because potassium has a 1+ charge, sulfate has a 2- charge. So we need 2 potassiums to balance the charge on the sulfate. And then strontium has a 2+ charge. Nitrate has a 1-. So we're going to need 2 nitrates. On the product side, just potassium nitrate. And then we have strontium sulfate. And that is our solid. Should be writing these in, aqueous, for everything except for strontium sulfate. Again, aqueous meaning dissolved in water. So where should we start in balancing this? Actually, better question, is there a right place to start? Not necessarily. You can kind of start anywhere. I think just looking at it from an overview perspective, you want to pick something that you're going to have to actually change. So off the bat, we can see that potassium, there's 2 on the left side, 1 on the right side. So we'll start there. So we'll add a coefficient here, right? Now that we have properly balanced compounds, we can't change any subscripts. So we just add coefficients. So now we have potassium balanced, 2 potassiums, 2 potassiums. But by adding this 2, we've also changed the number of nitrates.
May I have your attention, please? This is Atlas IED.
but we haven't changed the number of times that that announcement's going to go off. So 2 nitrates now, and we can actually look over on the left side on our reactants, and we can see that we already have 2 nitrates. So that's balanced, good. And then we'll check strontium. 1 strontium here, 1 strontium here, also looking good. And then finally, sulfate and 1 sulfate. So with just 1 coefficient there, we're able to balance it. So you could also go through and count up the number of each element on each side. You should come out with the same. Are there any questions? Nope. Cool. Should check. All right. So for these, we have 2 different types, or 2 different ways that we can write out these equations. As you can see from this previous slide, it's actually pretty helpful to have just all the ions spread out. Even without balancing them into compounds, we can still figure out if we have a product or not, at least in a precipitation reaction. So that's actually called the complete ionic equation. It's the equation that has all of the ions in it. The only compounds that aren't separated are solids, liquids, or gases. So those will stay as their molecular compound. So if you think about what we're representing here is how the ions actually are in solution. So if you add sodium chloride to water, it dissociates into the ions. So in our complete ionic equation, that's how we're representing it. But if we have something that's insoluble, like we have the strontium sulfate, that's actually not sort of exploded out into its ions in the solution. It's sitting at the bottom as a clump. The other equations that we've been working with have all been molecular equations, where we're showing the complete neutral formulas for each of the compounds. See some scribbling still. But actually, let me copy this real quick. Not that one. So from our net ionic equation, though, or complete ionic equation, excuse me, not all of these were part of a reaction. Some of them are spectator ions. So in this case, if I actually go through and I can, let me erase these, right? Only the strontium and the sulfate reacted to form a compound that was insoluble. Potassium and nitrate are still just hanging out in the solution. So those are called spectator ions. They haven't changed from one side to the other, from the reactants to the products. So we can actually just sort of cross them out and eliminate them from the reaction to give a more clear image of what's going on. So we can say, since potassium is the same on the left and right, and nitrate is the same on the left side and the right side, we can eliminate those. So our net ionic equation is SO4 2 minus plus strontium gives us strontium sulfate, solid. So it boils everything down to just the atoms and molecules that are participating in the reaction. So quick recap, molecular equation is a complete neutral formulas. The ionic equation, complete ionic equation, is all of the species as they actually are present in solution. And the net ionic equation is only the species that actually participate.
May I have your attention, please?
So if we have this reaction of hydrobromic acid with calcium hydroxide forming water and calcium bromide, let's write a complete ionic equation and a net ionic equation for the reaction. So this is sort of the reverse of what we did when we went from the names to the ions. We're now just going to go from these symbols to ions, being careful to note which ones are solids or liquids or gases. Right? Those are the only ones that don't get dissociated into ions. So in this case, and I like to also keep track of how many there are in the balanced reaction. So here we're given a balanced reaction. So it's going to be 2H plus 2 Br minus plus calcium 2 plus plus 2 OH minus. And then we're going to have still 2 H2O as a liquid, and then calcium 2 plus 2 Br minus. Let's do it. So this is the complete ionic equation. Right? It's got all of the ions, all of the species. So each species is like all the individual things as they are in solution. So now for the net ionic equation, which of these can we remove? Which species aren't participating? It's the ones that are the same on the left and the right. So going from the reactant side to the product side, they don't change. The order might change, but the order doesn't really matter. Yeah, calcium is one of them. So right, calcium 2 plus is also calcium 2 plus. So do you want to? Bromide? Yeah, bromide's the other one. So it's 2 Br minus, 2 Br minus on the right. So those are spectator ions. They haven't done anything. They're just sitting around and they're watching the hydrogens react with hydroxides to form water. This is also an example. I think it can be helpful to keep that sort of the coefficients for the balanced, from the balanced equation to your complete ionic equation. But sometimes you get to the end and it's going to simplify. So since we have 2 hydrogens, 2 hydroxides, and 2 waters, we can divide all those by 2. And so our final net ionic equation is just this. So you can see that really from even the molecular equation, which is this first one, there's a lot of extra stuff there that doesn't actually participate in the reaction. Any questions on these? Just remember if it's the same on the left and right. I think that actually, 2 things. There's remembering the definitions of complete ionic equation versus net ionic equation. If you're familiar with finance stuff, it's the difference between your gross income and your net income. So gross income is all the money that you make, so it's everything. Your net income subtracts out all of your expenses. So in this case, we're subtracting out the stuff that doesn't do anything. All right, so now we're going to sort of shift a little bit. Wow, back to back. It's a new record. So I really am just going to unplug those things.
What if it's actually important, though?
I have a very hard time, figuring out or justifying how it might be important. The clocks are even wrong. Is there one in here? No, there's not. I'm going to have to edit that out of the video. So we're going to shift gears and talk about some specific types of reactions. So let's start with acid-base reactions, right? Are a specific category where we're getting a certain combination of elements, kind of like we had a precipitation reaction before, right? It's a reaction that forms a solid. Acid-base reactions, also known as neutralization reactions, involve the reaction of an acid and a base. And they actually cancel each other out. So this previous reaction that we saw, let's go back here real quick. We had an acid, hydrobromic acid, and we had a base, calcium hydroxide. When they react together, acid-base reactions always simplify to this. The hydrogen plus hydroxide makes water. We'll learn more about definitions of acids and bases later. For now, the simple definition is that, as we learned in nomenclature also, acids have H+. Right? Their formulas begin with hydrogen. They also have a sour taste and can dissolve some metals. Bases, on the other hand, have hydroxide ions. I think hydroxide is on the list. I don't think we really talked about bases at all yet. They don't really have special naming schemes. It's just, for example, calcium hydroxide is just calcium hydroxide. The ones that we'll work with will almost all be metal hydroxides. So calcium's a metal here. Potassium hydroxide would be another. Have bitter tastes and feel slippery. So if you ever think you got some base on your fingers because you spilled some in lab or something, you can feel if it's slippery or not. And if it is, you should definitely go rinse your hand. If you don't think it's slippery, you should still go rinse your hand for a while. It's kind of like when you use soaps are not exactly bases, but it's kind of like that where you get it on your hands, right? You have to wash until your fingers aren't slippery anymore. The list of some common bases, again, or acids and bases. We talked about how to name some of these. Haven't talked about hydroxides, but again, they all have this OH group on them. So also called neutralization reactions. Again, it's really the reaction of this hydrogen with the hydroxide that forms water. The other compound here, though, is called a salt. And with that, you can make an assault rifle. Sorry, I'll go back to this so you can write this down. The joke's better that way, though. And this salt is not necessarily table salt. This is the chemical definition of salt. So it could be magnesium chloride, could be magnesium bromide, could be sodium bromide, a lot of different options. But it's the leftover parts of the acid and the base. All right. Yes, assault rifle. Yes. So again, we have acid and base forming a water and salt. So, and like I mentioned before too, the net ionic equation for many, not necessarily all, but for many of them is going to be H+, so OH- is H2O. All right, so let's write one of these out. This is where we start to get into predicting products. You can do that already with precipitation reactions. Right, we looked at those. You just take the cations, move them over, swap the anions, see if you get a reaction. That's predicting products. This is a very similar process. So we have our formulas here. So we've got sulfuric acid, so H2SO4, and that's aqueous, plus potassium hydroxide, also aqueous. And up front, you should recognize that, right, H2SO4 starts with hydrogen, it's an acid, and then potassium hydroxide has hydroxide in it. So there's two ways that you can look at predicting the products here. You could know that, oh, this is an acid-base reaction, we're going to get water as one of our products, and we're going to get salt. The other way you could do this is very similar to the precipitation reactions, where you think about our cations and our anions and swapping them. Now, in this case, we actually have two hydrogens on sulfate. If you wanted to, you could write this out as the net ionic equation and then swap them that way. Actually, since we have to do a net ionic equation anyway, let's do that. So we have our hydrogens here. So that'll be 2H plus SO4 2 minus plus K plus OH minus. So you can see here now more easily that we have cations and anions. So we can just move our cations over, 2H plus, plus one of the anions, right? So the other one. And then K plus our other anion. So hydrogen in the reactants was combined with sulfate. So on our product side, it's going to be combined with hydroxide. And then potassium is going to be combined with sulfate. Ooh. I think in this case, because we don't have a balanced chemical reaction first, it's better to leave off this 2, because otherwise you end up with 2 and 2, and then if you want to try and combine these and balance it, you could say, oh, we just need 2 hydroxides, and that's fine really, because you can get to here, and then you'll say, well, we'll have 2 H2O. But I think for the sake of, I think it's simpler to just write out the cations and anions, then do this combination, because now we just have the 1 H2O. And then our other product here would be potassium sulfate. And like before, where we needed to balance these appropriately, we do need 2 potassiums for this sulfate. So this will be K2SO4. Now that we have the molecular equation, actually I should write these in here too. So this is liquid and aqueous. Now we can balance our molecular equation. So where should we start? Is there an element that we should not start with? I guess to recap, the rules sort of were, if you have a free element, do that last. And if you have elements that occur in more than one compound on either side, also do those before you do free elements. So at the end. So in this case, it kind of doesn't matter. Really, for any of these, it doesn't really matter. But best practice, free elements especially, compounds that are in, or elements that are in 2 or more compounds, do those last. So in this case, we have hydrogen in 2 compounds on a reactants, oxygens everywhere. So we're going to leave hydrogen and oxygen till the end. So we do sulfate, because it's kind of, well, let's do potassium. I'm making this more confusing probably. So we'll look at all the reactants. We have potassium, just 1. We have 2 potassiums in our products. So we're going to need a 2 there. So now we've balanced that. We know this hydroxide is actually one of the oxygens, or is the oxygen that we moved over here. Also, again, polyatomic ions move as groups. So we'll balance this oxygen separate from the sulfate. So if we have 2 of these oxygens over here, we'll have a coefficient of 2. And now actually, if we balance that oxygen, then we can check our hydrogens next. So we have 2 hydrogens times the 2 in H2O, so 4 hydrogens total in our products. And then we have 2 from potassium hydroxide, and then also these 2 from sulfuric acid. So we have a total of 4 hydrogens in our reactants, and just the 1 sulfate. So it should be balanced. Let's double check. Hydrogen, sulfate, potassium, and oxygen. So 4 hydrogens, 1 sulfate, 2 potassium, 2 oxygen. This is for the reactant side. So hydrogens, again 4. We have the 1 sulfate, 2 potassium, and then counting these oxygens separate from the sulfate again, there's just 2 of those. So we have the same number of everything on both sides. So that is balanced. Man, the more I think about it, the more that writing out these ions first made things more confusing. And it's easier to just say, oh, this is an acid-base reaction, so we're going to have water, and then the leftovers here as the salt. Because now that we have that balanced equation, we have to take into account those coefficients that we added in our net ionic equation. So, and then even here, the hydrogens, we have 2 of those hydrogens there. We have 2 potassium, 2 hydroxides. And then here, we have a 2 coefficient. So it means we're actually going to have, oh, and that one gets confusing too. Oh, yeah. Because this won't be the net ionic equation unless this is water. Because the net ionic equation has everything as it is in solution. All right, yeah, I don't like that way of doing it. Okay, working from this net ionic equation then, what are our spectator ions? Potassium's 1. Sulfate, yep. So those are our spectator ions, which it is an acid-base reaction, so you probably could have seen this one coming too. but 2OH minus is 2H2O. So then we can simplify that. Like so. Do you have another one? No, we just go into gas evolution reactions. Yeah, so I would start with these, then predict that you're going to have water and a salt, balance that, then write a net ionic equation. Or complete ionic equation, and then the net. Are there any questions? Okay. A few more types of reactions to get through. Gas evolution reactions are reactions that make a gas. Some of them do this directly, so you can get hydrogen sulfide. So if you get sulfide and then a source of hydrogens like an acid, one of your products is hydrogen sulfide, that's a gas evolution reaction. That is the only one that forms it directly, though. The rest of the gas evolution reactions that we cover have an intermediate. So do it like this, highlight this. So there's the initial reactants. The red's fine, okay. Then there's this intermediate step in red, and then your final products will actually be this last step in blue. So when this reaction happens, you get an acid, hydrochloric acid here, and sodium bicarbonate. And then you get carbonic acid as an intermediate and a salt. But then this carbonic acid further decomposes into water liquid and CO2 gas. And that salt just kind of hangs around. So from the intermediate step to the final step, it doesn't change. So there are 3 of those that you have to memorize, and they're right here. So you have carbonates and bicarbonates. So carbonate being CO3 2-, and bicarbonate being CO2, or HCO2, 3, 1-. So either of those reacting with an acid will give you these final products: water, CO2, and a salt based on the starting products. So hydrochloric acid, potassium carbonate, you get potassium chloride. The other ones, or this next one is very, very similar. It's sulfites and bisulfites. So just like CO2, it's SO2 that you get as the gas. So again, also an acid reacting with potassium sulfite. So sulfite, SO3 2-, and bisulfite, H, SO3-. And sulfite. And you'll have some intermediate step with this intermediate product, H2SO3. The last one is a little bit different, where we have ammonium. Ammonium is the NH4+. So that ammonium reacting with a base now, so potassium hydroxide in this case, and you'll get ammonia as the final gas. I'll write that out. NH3 is ammonia. We'll do an example of this. So the key for gas evolution reactions is identifying those starting reactants as being any of the 4 on that list. So, and then if you get products H2CO3, H2SO3, and NH4OH, then those will further decompose. So you'll write the skeletal, go to the reactants, products, see that you have one of these. Then you'll write out the next step with those decomposition products. And then your final reaction will just be your initial reactants and that final step, and then you balance that. But we'll do an example here. So this is hydrobromic acid, so HBr, plus again, aqueous potassium sulfite, so K2, SO3, I always do this. So our products here, we're going to take the cations and swap them. So we're going to get H2SO3 plus potassium bromide and H2SO3, actually I should have done this, so I'm going to rewrite it, otherwise there's not enough space. H2SO3 can further decompose. So you say, okay, this is going to decompose, so we're going to get H2O liquid plus SO2 gas plus potassium bromide, aqueous. And then now instead of writing out this whole thing, we say all that really matters is this initial and then the final products. So your final molecular equation here, still not balanced, is going to be, now I can leave room for those coefficients. So it's the initial reactants and then the final products. So we don't write any of the intermediate. And these can be a little bit trickier to balance, just because the water for, well, the oxygen in water came from SO3, and so did the oxygens in sulfur dioxide here. So again, following that same rule, if we have a element that's in 2 compounds on one side, we're going to save that for last. You can start here with, let's just start with potassium, since that's different from this side to the other side. So we need a 2 on potassium bromide. And that means we're also going to need a 2 on hydrobromic acid, which gives us, so we balance the bromines there. We've also balanced our potassium. And now we can check our hydrogens are actually balanced there now. And then the number of oxygens is also the same on both sides. So we have these 3 in the SO3, but one of these oxygen, or this one oxygen came from SO3. These 2 oxygens also came from SO3. And then sulfur, also 1 on each side. This one works out nicely. Would encourage you at some point to just maybe take this one exactly, write this out, try balancing oxygen first. Actually, for this one, oxygen would already be balanced. I have to think of another one where oxygen wouldn't be balanced. But yeah, try at some point. Write some of these equations out. Try breaking those rules. Try to figure out when those rules actually matter, because they are really rules of thumb to try and make it easier. Okay. Any questions on gas evolution reactions? Okay. I'm actually going to skip some of these slides here because oxidation reduction is the bit of chapter 16 that we're going to cover. Briefly though, oxidation-reduction reactions, also called, and much more easily called, redox reactions, responsible for things like rusting of iron, bleaching of hair, also the production of electricity in batteries. Many but not all redox reactions involve the reaction of a substance with oxygen. So they're oxidation-reduction reactions. Some examples. This is the reverse of, you can take a battery, right? You take a 9-volt battery, put it in salt water. You actually do the reverse of this reaction. If you can get those two things if you get hydrogen and oxygen under the right conditions, you can power a space shuttle. But there's also the rusting of iron and the combustion of natural gas. And so all of these are reactions with oxygen. Redox reaction that does not involve oxygen would be one like this. We have sodium, elemental sodium reacting with elemental chlorine to make sodium chloride. What's actually happening in this reaction is there's an exchange of electrons happening. So most of the reactions we've talked about so far, we've got ionic compounds, and we're just swapping the ions around. No exchange of electrons, just exchanging those atoms. Oxidation-reduction reactions are this exchange of electrons. So oxidation is loss of electrons. Reduction is gain of electrons. So the mnemonic here that I like to use is oil rig. Oxidation is loss, reduction is gain. And you can't have an oxidation without a reduction of something else. So it's kind of like you can't have matter created or destroyed. When you take oxygen or you take electrons away from something, they have to go somewhere. So you can't have oxidation without reduction. And that's where I'm going to leave redox. Talk briefly. No, that's. Yeah, okay, so combustion reactions are a subclass of redox reactions, primarily reacting something with oxygen to form one or more oxygen-containing compounds, including water. Most of the combustion reactions, if there's a lot of carbons and hydrogens, will make carbon dioxide and water upon combustion. Yeah, combustion reactions are exothermic. Right? If you burn something, it creates heat. You can burn ethanol in alcoholic beverages. Actually, you can also burn isopropyl. Don't do this at home. This is my stupid story. If you put isopropyl alcohol on water, it's lighter than the water, so it'll float on top. You can light that on fire. But then how do you put it out? Well, a smart person would smother it. I was not that in high school. So I did this at home, went home for lunch, nobody else was home, had like a Pyrex like measuring cup, glass one, filled it about half full with water, put a bunch of isopropyl alcohol, lit it on fire. I was like, yeah, it's awesome. I was like, oh, I need to put this out. So I just dumped water on it, but it had been going for a little bit. So the glass had heated up on top. So when I dumped that in, the Pyrex just shattered and it exploded. And fortunately, that was enough to put out the fire. So don't do that at home. So in that reaction, you had not ethanol, but another type of alcohol. So basically this reaction, though, we got some sort of compound reacting with oxygen. Again, key here being carbons, hydrogens. There's some oxygen in here too. And you make CO2 and water. Octane, which is like the primary component in gasoline, just has 8 carbons, that's why it's octane. And all these hydrogens, when you react that with enough oxygen, which to be fair, almost never has enough oxygen, you get CO2 and water also. You can also burn methanol in race cars. Makes them go real fast. Shoot. All right, let's just real quick. So if you get a combustion reaction, C5, H12, this is liquid pentane, so you make that liquid, plus oxygen. Our products are always going to be here. CO2, it's going to be a gas, plus H2O, also a gas. And then you can follow really the same rules here for balancing. So you don't want to do anything that's in 2 compounds on either side, or that exists as a free element. So oxygen here, free element. So we'll balance oxygen last. We usually start with the first one, but let's start with hydrogen this time. So if we do hydrogen, we have 12 hydrogens here. So we need 12 on the right side. So we had a coefficient of 6 to H2O. And now we could go do oxygen, but we said we're going to balance oxygen last. So come back and we'll say, all right, carbon is the only other element present. We've got 5 carbons and just 1 in our products. Multiply that by 5. But now we have, well, I should say, now we've balanced carbon, hydrogen, oxygen's the only thing left. And the nice thing in these, especially these combustion reactions about doing oxygen last, is that by changing carbon, we also change the number of oxygens. By doing hydrogen, we also change the number of oxygens. So if we had balanced those at any point, we would have had to gone back and had to rebalance it again. But in this case, we have 10 oxygens, and we have 6 oxygens. So we need 16 on the left. So we can divide 16 by the 2 oxygens in O2. And our coefficient here should be 8. It takes a lot of oxygen to react with even a single pentane. Like 8 more slides. So up till now, we've talked about these classifications. Yeah, let's just hit these real quick. So classifying by what happens, right? What type of product do we get out of the reaction? In precipitation reactions, you get a solid. In acid-base reactions, you're going to get water plus a salt. In gas evolution reactions, you get a gas. And we haven't talked about oxidation-reduction reactions, but those involve an exchange of oxygens. The most readily identifiable are combustion reactions. Let me leave that for a second longer. Just a few more slides here. So we can also, instead of classifying by what happens, we can classify them based on what the atoms do. So in the case of a synthesis or combination reaction, we're combining two different things together to get a single product. In decomposition, we have a single reactant that breaks down into multiple products. Displacement reactions, we're replacing one of the atoms or molecules in one of the reactants. And then probably the most common are the double displacement reactions, where we have two compounds and we're swapping, I like to think about swapping the anions in those. So synthesis or combination reactions, again, key here being you're getting a single product. Right? Combining multiple things, getting a single product. Combining chlorine and sodium, for example, to make sodium chloride. Decomposition works in the opposite direction. This is that 9-volt battery reaction I keep talking about. So you're taking water, you have one reactant, water, and decomposing it into simpler products. Then for single displacement reaction, we'll talk about this a little bit more in terms of redox reactions. You have A plus BC. So in this case, zinc plus copper chloride. And then you get AC plus B on the other side, zinc chloride and copper. This is actually a process called, you can use this in a process called electroplating. In my COS class, you guys know why the Mad Hatter was mad? Because he did, what is it called? It's flame gilding? Yeah, flame gilding. So you can take an amalgam, so mixture of gold and mercury, and you can paint it on things. And then if you heat it up enough, the mercury evaporates and turns into a gas and leaves the gold behind. So you can gold plate things. So the Mad Hatter was mad because he breathed all the mercury. He was breathing mercury from putting gold on hats. Incredibly dangerous thing to do. And then double displacement reactions where you take your two compounds and then you swap anions to make two new compounds. And a lot of the ones we talked about today were those. So precipitation, acid-base, and gas evolution reactions are all forms of double displacement most of the time. What was this last slide? Oh yeah, just classification flow chart. So again, this is classifying by what atoms do rather than what the outcome is. And I think this last one is, oh yeah, we can go through these. These are real quick. So A, synthesis, decomposition, single displacement, double displacement. Single displacement, yeah. So we're taking the hydrogens here and we're swapping it with aluminum. So we get A, aluminum phosphate, and then hydrogen. So single displacement. How about B? Double displacement. So we have copper sulfate. We get copper hydroxide on the other side, but also potassium hydroxide for potassium sulfate. C, synthesis. So two simpler things to make something more complex. Process of elimination, D must be definitely synthesis. No, it's decomposition. So decomposition is the opposite of synthesis. Yeah, spelled that right. Okay. That is all for chapter 7.